So let's talk about high-level language constructs. So we've mentioned high-level language. These are languages like C, Java, and Python, where we can write our code at a higher level of abstraction, but eventually that high-level code is going to get compiled down into assembly language and eventually machine language, the ones and zeros, which we'll talk about later. So some common high-level constructs are loops, conditional statements, arrays, and function calls. But before we dive into those, let's introduce some instructions that support these: logical operations, shift instructions, multiplication, division, and branches and jumps. So Ada Lovelace, who was born in 1815, she wrote the first computer program, and her program calculated the Bernoulli numbers on Charles Babbage's analytical engine. And she happened to also be the daughter of the poet Lord Byron. So these kind of fundamental operations, logical instructions are used. So we have the bitwise AND, bitwise OR, and bitwise XOR. So these are bitwise operations, and is useful for masking bits. So for example, if we have some 32-bit value and we want to mask off everything but the lower byte, the lower 8 bits, then if we AND it with hex FF, well, all of these, 0 and anything is 0, get masked off, and all we're left with is the lower byte or lower 8 bits of that of the first operand. OR is useful for combining bits. So for example, if we have a register that holds that value, F234, and we OR it with a register holding this value, 12BC, then we're going to get the combination of those two, right? F234 is going to be ORed with these zeros, which will just anything or 0 is just anything, and then OR, and then those bottom 4 hex digits are ORed with those, and we get the 12BC. So we can combine those two values. XOR is useful for inverting bits. So if we do A XOR -1, remember -1 is all F's, we're going to get the not operation, so not A. Here's an example of logical instructions. Suppose register S1 holds this value and S2 holds this value. If we AND those together, that's first instruction, then anywhere we have, both of the bits are 1 in both registers, we're going to get a 1. Everywhere else we'll get zeros. And so, here we have all zeros, so clearly 0 and anything is 0. And the second instruction, we have OR, so anywhere we have a 1, here we have a 1 all the time in at least one of them. And so we get all 1s, and then this is all 0, so whatever is here will be the value there. Remember, this is a bitwise OR. And XOR forms the XOR of S1, S2, so 0 XOR 1 is 1, 1 XOR 1 is 0, and so forth. The bitwise XOR of those two registers, of the values in those two registers. We can also do logical instructions that have immediate operands. So here's the AND immediate, AND I operation, the OR immediate, OR I, and the XOR immediate. So this immediate, in this case it's a negative value, is sign extended before the logical operations occur. And so this is important because some architectures, many architectures actually 0 extend immediates before doing logical operations. In RISC-V, the 12-bit immediate is sign extended before it is ORed with the other operand. So sign extended, and then in this case ANDed, that first instruction ANDed with T3. And so we're going to get these results where we get the AND of, well, the sign extended immediate, right, only where we have both of them being 1. We're going to get a 1, dot, dot, dot. And then the OR of these two, T3, or the sign extended immediate, and the XOR of T3, XOR the sign extended immediate. So hex A34 is a 12-bit 2's complement representation of -1484. So here we have hex 3, 4. This is the 12-bit representation of that value. It is then sign extended. We also use shift instructions. The shift amount is in the lower 5 bits of a register. So shift left logical, shift right logical, and shift right arithmetic. And so here we have shift left logical T0, T1, T2 is, well, here's our destination register and our two source operands. T1 shifted left by the amount in T2, and specifically I'll write this in the lower 5 bits in that register of the value in that register. And same thing with shift right logical. Shift RL is the mnemonic. T0 equals T1 shifted right by the lower 5 bits of the value in T2. Shift right arithmetic, same thing, but we're going to shift in again. Arithmetic right shift is shifting in the sign bit when we shift right. And shift right logical just shifts in zeros every time. We can also have immediate shift instructions. So shift left logical immediate, shift right logical immediate, and shift right arithmetic immediate. And here we have an immediate that can vary from 0 to 31. So in this case, this is a 5-bit unsigned immediate. And so there we go. We can't do a shift left logical immediate of a negative value. This is an unsigned 5-bit number. So in this case, shift left logical immediate, T0 equals, well, T1 shifted left, shift left logical immediate by that constant value, that constant or immediate value. Same thing, same pattern with shift right logical immediate, T1 shifted right by 18 bits, shift right logical by 18 bits, and shift right arithmetic immediate, T1 shifted right arithmetically by 5 bits.